Should I start?
Yeah.
Okay. Any questions from yesterday? Okay. I should also apologize for how messy the explanations here about the identity relating K1 and K2 were. I did too many overlapping calculations in the same line, and it was a bit complicated. I wouldn't be able to understand myself. But the idea with that example was I really wanted to emphasize how the confluence of the properties associated with the pure spinor superspace leads to beautiful identities that you can prove in a few lines. Well, not if you count overlapping lines, but for example, one of the manipulations I did yesterday was I rewrote this factor here as the BRST charge acting on A1M minus K1M V1. And this rewriting here emphasizes, exemplifies very well what I was talking about, because you see that the BRST charge here acts very simply. It's closely related to the equation of motion 2 there. So it's basically the equation of motion. And the fact that these guys were inside the pure spinor bracket allowed me to integrate the BRST charge by parts and do these kind of manipulations. And in the end, all these facts together, they add up to something really nice in superspace. So there was a tendency in the beginning to look for a superspace expression containing, well, 3 lambdas and some superfields. And then you would try really hard to get rid of the pure spinors here using the measures and all that, but the attitude that you should have is you should embrace this type of expressions as your friend, because they really make the results compact, and they allow you to find nice identities. So yeah, so
this can be used for arbitrary endpoint function on the sphere?
Yes, and also the result of loop amplitudes can be written in this form. So for example, K2 and K1 from yesterday, they were coming from loop amplitudes that they computed. So the 2 loop amplitude and the 1 loop amplitude, you can also write them as pure spinor superspace expressions. And so a bit of historical remark, because when Nathan computed the 2 loop amplitude, he obtained that kinematic factor that I wrote yesterday. It was around March 2005, and sometime later he asked me to check what the component expansion of that expression would look like, because he wanted to check whether his result would agree with the RNS computation that was done by Docker and Funk. And it took me like 3 months to make sense out of the expansions and look at the lambda 3, 5 and compute everything. And in the end, I was making some mistakes, and but if you, and that was in the case that we were trying to get rid of the lambdas from the final expression, and then we compare the resulting component expansion. But if you simply work with the pure spinor expression like it is, then you can actually prove that that kinematic factor is related to the one loop kinematic factor. And in fact, in that paper from 2008, I also showed using superspace manipulations that the K1 from the one loop amplitude is proportional to K0, where K0 comes from the tree-level amplitude. So just from a few lines of computation, you could actually show that the two-loop amplitude had the same kinematic factors as the tree-level amplitude without doing any component expansion, just using superspace. And that works for all the fermionic components as well. So it's something that I cannot emphasize enough what a difference it makes if you just don't try to get rid of the numbers. But of course, it's very useful to be able to do that when you want to check some things. But it's not the essential point. So today I'm going to actually start with the solution for the endpoint tree-level string amplitude. And I will do that by computing the one OPE with V1. Okay, I will compute the OPE among vertex operators, and I will show to you how one can identify a recursive structure in these calculations. And once you have a recursion, then you can easily go to endpoints, because the recursion does the calculation for you. In that paper in 2008, there was also the computation that I'm going to do here today. And so I will first start with rewriting what I wrote yesterday, because I had hopes that I would arrive at the point that we are now, but so I will just rewrite the OPEs that we're going to need in this particular calculation. Okay, so these are the OPEs, and if you remember the tree-level prescription for the amplitude.
In the first equation, shouldn't that n be contracted?
Where? Which?
Index name, Km.
Km.
By
Ah, okay, yeah, there is a phi m.
Oh.
Thank you. Yeah, whenever you look something strange, just interrupt me, and it's helpful. Okay, so the amplitude prescription is this one. And that is one. And for the sake of clarity, I will keep the positions of the unintegrated vertices unfixed, just to be able to keep track of them. Except for this one, which is I accept it to be at infinity. And of course there are a bunch of integrals over these positions, but I'm not going to write them. So this one is at infinity. And okay, so these numbers here are the labels of the particles. And so you see that in order to evaluate this correlator, one of the tasks that you need to do is compute an OPE between an unintegrated vertex and the integrated one. Oh, and I should write the form of the OPEs, just the vertex of vertex. So I guess this will be the last slow computation that I'm going to do. And
okay. Should be integrals over the
what?
Integrals over u's.
Yes, there are the integrals. So you need to integrate over the positions. You see 2 up to c n minus 2. But well, I'm not writing the integrals here, just to save some space. And okay, so what we are required to do is these OPEs. There are other OPEs to compute, but this is one of them.
In the RNS formulation, one can get the unintegrated vertex operator from B and VOP.
Yes.
Is there an analog here?
No, there is no analog here, but from yeah. So the analog of that relation here, well, that relation, let me remind myself, it's BV equals U, something like that, right?
Yeah.
Yeah. So from this relation, you can actually obtain that Q of U is del V, right? Q is the BRC charge on both sides, and Q of B is T, and becomes del V acting on V. So So because that back in 2000 there was no V ghost, then Nathan used this relation here to map these words. So because the B was absent there. Okay, so let's compute this OP. There is just a simple pole, and let me just try to get the signs correct for once. So Z21, Z ij is Zi minus Zj, and so you need to use the OPs here, and this field here has no OPs with anything there, because there is simply no conjugate momentum to theta there. So this guy here for this particular calculation will not matter. So forget about that term. And when you compute the OP, now okay, so let me let me just okay. When you use this OP here, you will simply pick the momentum 1 of that vertex there. So the first term here is you will get A2M because of that, and then K1 1M V1. This term simply picks the momentum of that particle. And that's, I will call this term number 1. So now the OP of this guy, d alpha acts as a covariant derivative, and you will get minus W2 alpha d alpha acting on V1. That's the OP2 from that part. And similarly, the OP of n with lambda will give you minus 1 over 4 and n A1 F2 Mn. And that's term number 3. Okay, so that's the result of the OP. And this is correct.
In this case, you are only considering massless vertex operator?
Yeah, yes. So these are the vertices that contain the gluons and gluons. So this computation as written here is correct, but it's not convenient. So why I say this? Because, for example, you see there is a covariant derivative here acting on V1, and so the A alpha field inside V1 there, the equation of motion does not really get rid of the covariant derivative, because you act with covariant derivative, there is also another term with a covariant derivative. So this term will be, it's simply, well, it's not pretty to have this covariant derivative. And similarly, this combination here where A alpha is not contracted directly with lambda, like that, is also not really convenient to work with, because, say for example, you compute the BRST variation of such term, you will also arrive at this problem. You will not be able to get rid of the covariant derivative from the BRST charge. So it's correct, but it's not convenient. So let's make this result convenient.
And you want to get rid of this covariant derivative.
Why do I get? Why do I?
You want to use those equations.
Yeah. So for example, if I say that if I define this as, say, L21, I want to ask you, what is Q acting on L21? Do this computation. This term will work okay. So you compute Q of A. It was on some the same identity that I wrote there. So it works out okay. But then Q acting on this guy. So what do you do when Q acts on this guy? You can try to anti-commute the Q, the D here with D there, and you could try some things, but it's not really in a form that you can immediately do the computation. And what I'm going to show to you is how you can use the cohomology structure of the pure spinor bracket to rewrite this expression here in a convenient way, where this computation here will be immediate. So that's one reason. It's a technical reason, because I'm sure you can compute that thing as well, but it's simply not in a convenient form. And when you're trying to solve for the endpoint amplitude, every single step where you can simplify something, you should simplify, because the simplification that comes from here will propagate to higher points, and yeah, so that's you should also you should always stay hungry looking for simplifications, and because in the end they pay off. So so let's look at this term here, the term that I said it's not convenient. One way you can handle the term is, well, I'm just going to rewrite it as putting the Spinor indices very explicitly. Like this. And now you see, whoa, there is a lambda beta here and a beta there, but beta. But we know that we always want to find the BRST charge somewhere, because we want to integrate by parts. So what we are going to do, we are going to use the first equation there. So rewrite this term as minus d beta alpha, d beta a1 alpha plus gamma m right? Because so I use the equation of motion 1 here. So this term becomes what? It becomes now it's a plus sign W2 alpha, and then lambda beta d beta is the BRST charge acting on A1 alpha, like that. And then minus lambda gamma W2 A1N. Okay, so now you will see the BRST charge, and this calculation is inside the pure Spinor correlator. So you are allowed to use integration by parts of the BRST charge. So let's do that with this term here. So okay, so that was term number 2 becomes that. So let's keep this term. It survives, and let's integrate the BRST charge by parts over there. That is minus Q acting on everything. So I'm going to write with parentheses, meaning that I contract the Spinor indices. And then, okay, in general there are more stuff that will be here. So let me call that other stuff M. So it's M like that. and then plus or minus, let me, plus. So now Q, I need to subtract when Q acts on W, and then I use the equation of motion 3 over there to get lambda mn A1 F2 mn. I use it, the equation of motion 3 here. And now you see that this term cancels that one. So, and this is 0 because everything is inside the correlation. So, 0, and that term cancels this term. So, what you get in the end, you rewrote the OP V1 U2 becomes C21 minus then V1 K1 dot A2 plus lambda gamma M W2 K1M. Visually, well, that's okay. So, yeah, okay. This minus sign is okay. So the minus signs are correct. So just visually, you can already notice that this result is more convenient than that, and it also feels better to get rid of BRST trivial stuff in the process. So now let's do what I told you before. Let's define this as actually minus L21, and just out of curiosity, let's compute. So let's define this as that, and out of curiosity, let's compute what happens with that guy. Compute Q on that. Okay, so that the first term will be there will be an overall plus sign because of that. And then I use the equation of motion 2 there. I get K1M lambda M W2 plus V1 and then V2 S12. S12 is the contraction of K1, K2 from this term. And I do the same thing here. If you remember from yesterday, this factor here is BRST closed, so you just add with Q here, and you get a minus sign because W2 is fermionic. So you will get minus lambda gamma M W1 plus momentum 1 contracted with V1. Not contracted, but it's there. Right? So that's the computation. And now, let me just rewrite this more clearly. M. So now, remember from okay, so this term here cancels that term on the spot. This one is plus sign and this one is minus sign. Oops. Okay. Whoa. It's not really. I'm okay. I messed up the sign because I forgot this minus sign here. It's plus. So I get plus V1 W2, and this term is plus W2 V1, but W2 and V1 are fermionic, so I commute and then the sign cancels. So these two terms go away, and if you remember from yesterday, the identity of lambda gamma M that this term here is 0 by the pure spinor condition. So, so the end result is that Q of L21 S12 V1 V2. And that's a nice result. I mean, it's but who could expect such a structure from the OPE? But actually, well, I shouldn't say this because, well, I'm going to show an argument from a paper that I wrote in 2010 that, well, it's a hand waving. Okay, but I have an argument to understand this structure here, but I'm going to mention that later. So okay, so let's since we got a nice result, let's try to analyze this more. So what will happen with if you compute Q of L21 plus L12? You get 0, right? Because if you want V2 and commute. So you learn that the symmetric part of L21 is BRST exact. It's BRST closed. So it makes sense to get rid of this symmetric part simply because yeah. It's BRST closed, but it's also BRST exact. So and it's actually expected to be because this guy has conformal weight different than 0. So I won't do this computation here now, but if you compute Q on A1 dotted to A2, you get precisely that combination. So the symmetric part of this guy is BRST exact. So let's just for fun remove that part and define V12 as L21 minus 1/2 Q A1 dot A2. Right, so in I'm just removing the BRST trivial part, and this guy still satisfies the same equation, the same relation. Okay, so well, it's nice because now V12 is anti-symmetric. We start to see some structure, but now we can do more. We need to do more because this is the result of computing this OP here. But then there is still a bunch of other vertex operators, and in particular, the next one that you can compute is U3, but now U3 will act on this L21. So you should compute the OPE between L21 and U3 now. And I won't do the computation, but simply I'm not even quoting the result here, but I will just so this guy is sitting at Z1, and you want to compute this OP here. And you can do the computation. I did this in 2009, 0909. have some numbers here. And well, you get some result. It's a bit longer to write down, but what is the interesting thing that happens there is you just do the same type of reasoning. What happens if you define, if you say, well, let's define this as L2131, the definition of this OP here. And then you compute Q of what you got there, right? And if you do that, you will get K1.
This is the coefficient of the pole?
Yes, yeah. It's the simple pole. How can I write this? It's the thing that sits inside over on top of C31. So that is the definition of L131. And it's a bunch of superfields, and you compute Q of that and use all types of identities to simplify and the result, and you will get this answer. You will get L31 V2 plus V1 L32 minus or plus K12 of A3 L21 V3. Okay, well, it also looks nice. You see, you are starting to see some kind of algebra because it's just the objects that you had before that are appearing here. And similarly, you can study the symmetries of these objects. Actually, you should do something more with that guy, because you see that there are L21s appearing here at 3.1, but we already know that you can redefine the L object by subtracting the BRST exact quantity. So you should subtract the BRST exact quantities that come from here, and then you get some redefinition of Q here, of L2131, in such a way that when Q hits this redefinition here, the end result is that you replace the L's by the V's.
Okay, so K12 is K1 minus K2.
Okay, thank you. It's K1 is plus, and in general, okay, so right, that's also a good point to emphasize the notation.
Okay, so could you please repeat what you said, the last thing, this
Oh.
N2131 plus something?
Yes. I computed the BRST variation of this object, and the right hand side has L's. But as I said, the V object is nicer in some sense than L, because I already got rid of BRST exact primes.
Yeah.
So you should try to get nice things
Here is the exact part.
in your computation. So what you should define here, I forgot exactly the definitions there, but they look more or less like it will be plus 1/2 K1, 2, 3, and then from that part you get A1 dot A2 V3, and you get some other terms coming from here, right? And the claim is that this object here now is the BRST variation of this guy will be written in terms of V's instead of L's, because when Q hits here, you simply remove the BRST exact part from that term, for example. And you do the same for these two other terms, and you get rid of the BRST exact parts there.
So that expression is Q acting on L or
Yeah,
only
yeah,
L?
it's Q acting on L. So that's why you can redefine, because you simply write these as V12 minus Q A1 and A2, and then you simply move that to the left hand side. So it's a redefinition of L2131.
Oh, you want.
Am I going too slow or?
I know. Supposed to have dedicated.
So with that state, like all the terms in the right hand side can be written as a V, like you have also L31 and L32 also. Like in your that expression in the box.
Yes.
L31, L32.
Yes,
All of them can be.
it's also the same thing. You get you write these as you subtract the BRST exact part from here, and you move to dollar sign. Okay, so I'm just going to mention something right now that will sound a bit that I will be jumping too much, but when you do the computation, say for the 5-point amplitude, you will see that this type of redefinition happens automatically, because this guy here will be related to the double pole in our OPE. Okay, not particularly this one, but there will be terms like redefinitions involving A2, A3, some V1, and some momenta here. And when you compute the OPEs now between the integrated vertices, so say you compute the OPE between U2 and U3, you will get some a simple pole here and a double pole. And the double pole has precisely the form of A2, A3. And there are also other terms that are related to the term that I described there. And I'm going to show later that the integral of the double pole can be rewritten as a sum over integrals that do not contain double poles by using integration by parts. So what happens is that these terms end up redefining what you have in the simple pole that you get from the simple poles. And once you see this mechanism happening for the first time, you say, whoa, there is something quite magical happening. And I forgot to say that the double pole here will contain a factor of 1 plus S23. And well, to see this that this factor builds up, one essential point in the calculations will be something that Nathan was referring to this morning, that the level of the NNOPE is -3. So this -3, if it wasn't -3, then you would not get this this term here, and this term is precisely the one that's necessary to integrate by parts. So you see that all these things are working in your favor, and the end result is quite remarkable. Okay, so I jumped ahead a bit, but just to increase the level of motivation.
I didn't get what you do after you push all this BLSD exact terms on the left and combine with L
Yes.
and get the right hand side written in terms of V's only. And then
Yes. So I'm a bit hesitant to. Okay, so when you do this, you will get an object that you will define as a V tilde 1, 2, 3 or V hat. So the idea with this Q V1, 2, 3 hat is that one that now you will get the BLSD variation written in terms of V's only, right? It will be that structure but replace it with V's. But you see that there is a hat here, and I should explain what this hat is, and that's what I'm going to do next.
this is analogous to V12 for the next level, right?
Yes.
This V12 that you define there.
Yeah. So
Without hat.
yeah, there is no hat here because this guy already is anti-symmetric.
Okay, I see.
And this guy here, what are the symmetries of this object? And the head here is related to a failure of the desired symmetries that you would like this object to have. And this is related to BCJ.
So this will always have S12 as a p-factor?
Oh, yeah. Yes, if you start with the 1 and 2 labels, then the first term will always be of that form. But I will write down the general expression for the general V that. But it will take some time because I need to explain the hat and the definitions, and I realize that this is technical, but it is what it is, because the end result is that you get the endpoint 3 amplitude. So but that's not okay. I said that okay, so
Sorry. So in the box is Q B hat 1 to 3, right? Or I don't know.
what?
Is Q in B hat 1 to 3?
B hat? Oh, okay. Yes.
Yeah, right.
Yeah. These redefinitions here are the same ones that I said that it's B hat. So yeah, it's
Okay.
B hat. But okay. I realize that now I made a pedagogical mistake because I included the redefinitions here. Well, if you consider this line as the redefinitions, but I didn't change these to V's, so you should not do that. So this one, the right hand side here is just the Q of L, and when you put the redefinitions, then it becomes V's.
So all the L's become V's.
Yeah. So but you need to redefine L.
Okay, so that expression Q here is basically that expression with L.
Should I rewrite that or
No, it's okay. I think.
it's okay? Right? Mm.
In this last time, if we replace L21 by V12 plus half, shouldn't there also that is exception?
Yeah, there is something. Okay, in this case, there is no really magic going on because V with a single particle label is BRST closed. So when you redefine that guy here, the Q does not act on V3, but in this case you can put V3 here inside because V3 is BRST closed, so you can move everything there. But starting with the rank 4 case, L21, 31, 41, this will no longer be true. There will be terms like L21, L31, and then when you redefine things, yeah, it's but it turns out that there is some magic going on that you can actually put everything inside the same BRST variation and move to the other side. The extra terms cancel.
Whatever is left will call the V. Whatever is left, that will
Yes, it's. But I'm going to show. I'm just going to very briefly mention the arguments that you can use to convince yourself that you will get a nice BRST algebra like that. So it's a somewhat hand-waving argument, but so that's why say you define L21 as this OP here, and you compute Q of that, but let's compute Q of that before doing the OPs there and see what happens. So V1 is BRST closed, so you act only here, so you get minus V1, and then when Q hits U2, that's del V2, right? And now, if you remember from yesterday, you can rewrite the covariant, the derivative on with in terms of z's as like this. Right? And then now you compute the OPs from this expression. And this term does not contribute, and this term will simply pick the momentum 1 there, but then there is already momentum 2 here. So you get minus S12 or plus because of the sign in the OP. So you immediately see that you get something like that. And you can iterate this argument, because now let's do this. And Q hitting here gives you that, so S12, V1, V2, but now you need to compute the OP of that with U3, and then minus L21 del V3. And this term here, by the same argument, will pick the momentum of this guy. So it in the end you will get minus or plus K12, K3, V3 from this guy here, L21 there, which is this term here. And similarly, and now you compute the OPs of these guys. So when U3 acts here, you get the L31. So L31 V2, and then plus or minus V1 L32, which are those two terms like that. So it's a simple simple way to understand what you get as a result of this computation, because actually going through the computation here and then computing Q of that starts to become messy. And for example, the rank 4 case already starts to blow up. So it's nice to have a simple argument to understand what's going on. Okay, sorry. Okay,
So V1 del V2 OP, when you calculate this first term del theta, that doesn't contribute. But the second term pi m contracted with V1 is giving you K1. Is that?
Yes.
Okay.
Because of the OP that was written there. Okay. So one thing that I just briefly mentioned before, but now I'm going to be is that in these computations you also need to compute the OPs between integrated vertex operators, and that's a bit more complicated. So that's why I'm not going to attempt this here, but it's in this paper 0909. Some numbers here.
So is the idea that by knowing the OPs you will write down the correlation function first and then you do the integral?
Yeah.
Is that what you're trying to do?
Yeah.
So you will determine the correlation function just in terms of the OP.
Yeah. And as I mentioned before, there will be some manipulations involving the double poles that are essential to the simplification. When you compute these OP, so these are conformal weight 1 variables, so one result here that will be a simple pole will have conformal weight 1, and it turns out that it has the same structure as one integrated vertex. So I'm going to do the calculation. I did the calculation, and you define whatever is multiplying del theta by you define it to be something like that. A alpha is now 2 labels, and the same thing happens for this superfield and the others. So the D F. So now I can uncover this. So when you do that computation, say for example for 1 and 2 there, and you read off the coefficients of those terms, this is what you will find. I hope. Okay, well, yeah, the very precise form of these terms don't really matter, because I could also have made some typos here. So, but it's just the structure that it's nice to see, and say for example the A alpha 1 2 that you get there has this minus 1/2 and that term here, and this term, if you remember, it's precisely the V12 that I had before. So the 1/2 comes from the subtraction of the BRST exact part, and that's what you get. So you recover the same calculation that you did for V1, U2. And then you get a multi-particle superfield with that corresponds to the AM and then the W alpha and FMN. And you see the FMN has a very nice structure because it is the expected generalization of a field strength. It's the momentum times the vector polarization. So it's now 1, 2 and 1, 2, and then there is some correction that depends on the conformal weight of that guy. But so there is something nice going on. Well, actually, you still, well, and as I said before, there is also a double pole here. Of that form, roughly speaking. And we are going to deal with that later. But perhaps not even that, because I already mentioned what will happen. But so what's the nice thing about those particular combinations that appear there from this computation? You look at these terms, and you know the equation of motion for the linearized fields, and just out of curiosity, you compute these. You try to understand what's the equation of motion for those objects. Symmetric that. And at this point, it's a lot of calculations. But the end result is nice. And the same thing you do for AM. Is it clear what I'm doing here? I'm just computing the covariant derivative acting on those combinations and using those equations of motion. And I get these terms here. It's at this point this is just purely mathematics. It's there's nothing mysterious here. Okay, I'm not going to write everything, but okay, there is also some other terms here. You can read the full expressions in this paper. It's 4986.
A12 is different, same one.
Yes, that's. And so what's remarkable about this? You see that the equations of motion, they are replicating, or they are similar to the equation of motion for the single particle. Say, I just put one label here for one particle. they have the same structure, exactly the same structure. Except that you get some additional contact terms, but the contact terms are very well behaved. And
It's plus, right?
it's,
A alpha 1, A beta 2 plus A alpha.
no, it should be
Asymmetric.
okay.
No, 2, 1, 1.
Asymmetric.
Yeah, it's anti-symmetric in 1 and 2.
And in alpha beta asymmetric, right?
Yeah, okay, you can also, well, I'm just going to write the same thing, but you can also write this as plus 1 beta 2 alpha.
They are primarily, right?
Yes. But okay, again, when you start to see these structures, you realize that okay, there is something going on that was hidden from just looking at the prescription, and then you do some more of these computations. Say you go up to rank 4. And you keep on seeing the same patterns repeating again and again. At some point you are simply convinced that okay, that's going to be true forever. And it turns out to be the case, and I'm going to try to motivate that now. But one thing that it's important to, well, it's just notation, but it's important to have a good way to handle more and more of these objects.
So when you define this A1, 2, etc., you define it from UU, right?
Yes. Yeah. Well, actually, this guy can also be defined as coming from V1, U2. And then that's essentially that guy. But this guy appears also inside this OP here as the coefficient of del theta.
Okay, and when you do that, when you define this way, you have done the construction. V1, U2, two operators at 2 different points.
Yeah. So
contracted.
yeah. So now this is sitting at 1 point only.
Okay, so I see. So
And then when you expand the plane waves of that guy, you will get something like I k12 dot x.
UU is supposed to have what kind of pole structure? Single pole.
Yeah, the UU has a single pole and a double pole. Something like that. And
These results are single pole results.
yeah, these are the same.
Single pole.
You see, these are the same objects that are here.
That's right. Yeah. Now, what do you get in the double pole? Is there any relation with this?
Yeah. What I get in the double pole is something of this structure here. So let's. Okay, since you asked it, let me just do this, and then I want to that when I do the string correlator. Well, I'm already doing the correlator, but that you get, for example, the double pole of U2, U3 will have this form, and there's a lot of computation involved here, but in the end you can simplify to that form. And let's look at this factor here. I didn't mention before, but in doing these calculations, it's very convenient to keep the plane waves as to the very last step of the calculation. So you compute you replace the correlator only at the very end, and this is at it's called the Kobayashi factor. And for the three-level amplitudes, it looks like this. It's Z I S I J, and now the it's plus or minus, and I never really sure because yeah, I equals 1. But that's the only place where I'm sloppy, because if you do any sign mistake somewhere, or you're lost, you don't see any structure. But at least at this point it's localized to that. Yeah, okay. So that's the Kobayashi factor, and let's say I define this to be like that, Kobayashi. And something interesting happens, because you know that the correlator will always have that factor, and the correlator in particular will have these integrals. And now you can ask yourself, what do you get from, you get 0 because it's total derivative, and just compute this of the Kobayashi factor. So it's 0 because it's a total derivative, and that. So what you get from this calculation is something like 1 plus S to 3 Z to 3 squared, and plus 1 over Z to 3, and then multiplying, say, S 1 3 over Z 1 3 plus S 4 3 over Z 4 3, and so forth. It depends on the number of points there. Right? That's just everything multiplying the Kobayashi factor. It's just an identity. And since the whole thing is 0, now you can rewrite that double pole integral as a sum over simple. I should not say simple poles, but it's something that doesn't contain squares of the worksheet function. It seems that you will see from the simple pole OPs recursive like that, because, say for example, you know what I mean. So that's how you get rid of the double poles. And what happens is that once you do this, these are precisely the combinations that I mentioned before that redefine these guys here. Because in the amplitude, when you compute everything, you have some 2-1, Z3-1 plus all the terms, and then there will be the double pole, something like that. And with 1 plus S. And then you use that identity and you get the definition for these kinds. And so what the string theory is doing for you is that it is kind of enforcing nice scarcity properties on your result. That's one interpretation. The other interpretation is that this integral here, the z with a double pole, has tachyonic poles. If you simply expand in if you do the alpha prime expansions, the first term will be something like 1 plus s to 3, and then plus some higher alpha prime order. So this is a tachyonic pole, and what string theory is doing to you is that it's saying that you don't really get the tachyonic poles in your amplitude, because the only source of tachyonic poles is that guy, and you can rewrite in terms of things that have no tachyonic poles. So that's one way of seeing that there are no tachyons. Okay, that's a lot of information.
But it's not possible to formulate in a way where you never have the double pole?
What?
Is it possible to formulate it in a way where you never encounter the double pole?
Well, the double pole is there. You cannot avoid. When you compute the correlation function, there will be terms like this. But
Two integrated vertex operator will always have the double pole.
yes, but they always appear in a nice way that allows integration by parts to take place. And what I will describe later is an effective way of doing these OPEs where you will never see this double pole, simply because I will immediately write down the coefficients of the simple poles using the V's, where the L's becoming V's are related to the fact that these will always be rewritten, but will redefine the simple poles. But it's something that okay, so this was first noticed for the 5-point computation in 2009, and in 2010, together with Oliver and Stieberger and Dimitrios Tsipis, we also verified that at the 6-point level you get also some structure for double poles that allow integration by parts to take place. And then we did some preliminary calculation for 7 points, and that was also happening. So at that point we said, okay, that's going to be true in general. But, and then the argument with the tachyon cancellation simply gave us confidence that we are safe to say that. So yeah, double poles from now on they are gone.
Sorry, what about the contributions to the amplitude which are not from the OP? That follows separately? Because you are existing everywhere in the OPs, right?
Yes.
What about the contributions to the amplitude not from the OPs? Because apart from the singular terms, there are also terms where you go to 0, right? So everything cannot be boiled down to OP. What about those?
Well, no, not really.
U has integral, right? So pick up the right poles.
But using analyticity, basically they are determining the correlation function completely. If you know the function and all its poles, right? And it goes to 0 at infinity.
This is, you have kept the 1 by z term, plus the order 1 plus order z term, order z square.
Yeah, but those you can use these analytic arguments to show that they are 0. So you don't get any non-singular functions, at least at tree level, like that.
See, if you have a function whose zeros and whose all its poles are known, and the residue is known, then the function can return in it. So
But this is not going to be the final answer. You have to complete it, right?
yeah, but you have to write the function
Which has these as the correct.
yeah, which has these are the correct poles. But you don't need extra information. Because
but
as long as we demand the function is going to zero at infinity.
right. So, but you have to write down the function at the end which has these as the poles.
Yeah. Yeah.
So, in other words, this is not the complete answer. You have to write down this function of
That's yeah, then do it.
which actually has these as the poles.
Yeah.
Please processing. That's on sphere, and Narayan did the same thing on Genesis.
I just want to make a brief remark, because I'm kind of...
one question. You said that double poles are all gone.
yes.
So this thing you are writing, that double pole you are writing the other part, right? Minus of this
Yeah.
thing. So then you said why is it gone? I mean, they are there.
Well, yeah, they are there, but you never consider the double poles like this. You say that, well, this double pole is that part, because then you get 0 is this plus that, so
Yeah.
you never really encounter these kinds anymore. And
This contribution.
this contribution is precisely the ones that transform the L's to V's. So these are observations that happen. The L's becoming V's are related to these redefinitions that happen when you get rid of the double pole. So one way to do the computations efficiently is that you never consider the double poles, and whenever you compute the OPs using simple poles, you don't write L's but write directly the V's. So when what you are doing is that you are doing these calculations automatically.
So finally you will get V hat 1, 2, 3, 4, etc.
Yeah, but it's not really V hat. It will be just V. But yeah,
So when you have to calculate an endpoint function, you will first construct the integrand as a function of all the z's. Is that right? For endpoint function,
yes.
you will first write down the integrand as a function of all the z's,
Yes.
and then integrate, or you will do this.
Well, doing the integrals is a different business. You really need some.
So here you are always analysis being done on the integrand.
Yeah, it's the integrand level, but nowadays, due to the work of Stieberg and Oliver Slaughter, everything that you need to know about these integrals, they know. It's you get these. There is a very nice structure that they got. They found these MCVs in the alpha prime expansions, and it's very beautiful, and everything is known. So if you just want to get some results for these guys here with some, say, alpha prime the power 12 or something, these guys are known. But the last thing before the break that I just want to mention some conventions to talk about multi-point labels, because let me just we arrive at here using some type of recursion, right? We computed L21 and then with U3 and arrived at L21, 3-1 and so forth, and you can do that forever. And what happens is you get these fields like that, and The labels will simply be replaced by general labels. So for example, the 1, 2 here will become a general PQ, where 1 here becomes a P, capital P, K1 becomes capital P, Q, and then you anti-symmetrize P and Q. And you get this structure for all of these superfields. And where now P and Q are denoted the multi-particle labels. So say for example P, capital P could mean 1, 2, 3, 4, some arbitrary label, or it could be 2, 3, 1, 4, something. Right? The definition of, these are called multi-particle labels.
So Kp will be K1 plus K2 plus K3 plus K4.
Yes. The momentum associated with a superfield with label P, the momentum of this guy will be Kp, where Kp with a multi-particle label is defined as, well, whatever the labels are there, you sum it. And this is a very, very huge step. It's you go from single particle labels to multi-particle labels, and what you get is essentially the same equations of motion. You just replace P and Q here, and you modify the contact terms, but the modifications of the contact terms, we know the general structure, and I'm going to write down after the break. But
so since you haven't done any integrals, so you will be keeping all those arguments somehow, right?
yeah, the z's.
Yes. So how does it appear?
Well, they don't appear here.
But they're
The z's are not here. They are just
superfields only.
they are just a superfield.
Oh, I see.
There is
I see. No, but
Well,
there was a vortex operator after you take this, you calculate the single pole. Along with the superfields, there should be a vortex operator at one of the points, right? I'm confused about that.
But
You see, you did L21 U3. From there you go to L21 3, right?
Yes.
Another contraction.
the capital is equal.
Yeah, but what vortex operator? What?
2, that becomes L21. At that point, there is no V1 anymore. There is no U2 anymore. The information that you had before from particles 1 and 2 are in this multi-particle label now.
I see, the residue has only the superfields.
Yes. So what you are doing here is you are actually doing the OPEs, and you are getting a result in an organized way. And as you can see, the definition of the PQ superfields is fully recursive, because, well, I didn't mention what you should put here when there is no brackets, but I'm going to do that later. But you see that it's recursive, and if you actually expand the, say, a superfield with 4 labels, say 1, 2, 3, 4, you already get quite a mess here, and you get like, I don't know, 30 or 40 terms, and it simply becomes it increases very quickly
So A12 without bracket is not the same as A12 with bracket?
Okay, right, so the convention for a naked label without brackets is say like capital P being P1, P2 up to Pn. It's defined as the bracket where P1 up to Pn minus 1 and then Pn. When you see a label like that, say 1, 2, 3, 4, that's actually the bracket 1, 2, 3, 4. And yeah.
So it is 1, 2 is the last equation.
What?
So this last equation A1, 2.
This?
Yeah.
The
So
first
A12 will be the same as A1 bracket 2, A bracket 1.
Yes.
A, the first term in this equation, A1, 2 represented.
Oh yes. So that one is actually the same thing as you said. So now you see that you get a proper recursion because you know what the single particle labels are, and then you can construct the multi-particle ones from these definitions. And a lot of
So suppose you have P as one of these complicated structure and Q as one of these complicated structure.
yes.
Then AP comma P bracket Q is some complicated structure, right?
Yes.
So that never appears in the naked object, is it?
Say you
Yeah.
something like this 1, 2, and then 3, 4.
Yeah. So this never appears in the when it recurs.
Naively it appears, but when we come back, I will show to you that there are the symmetries that I didn't explain for the V hat becoming V, and these definitions here will tell you that this guy here is actually 1, 2, 3, 4 minus 1, 2, 4, 3. So that's the same thing as 1, 2, 3, 4 minus 1, 2, 4, 3. And it's essentially a Jacobian.
So those are sufficient. Everything can be expressed in terms of those.
Yeah. So and now we arrived at these patterns here by some trial and error and trying to find nice structures. But nowadays we understand the transformation of these brackets to things like that as a change of gauge of these multi-particle superfields. There are gauge transformations just like the single particle ones. There are multi-particle gauge transformations that you can use to impose these symmetries. And for reasons that perhaps will become clear in the next lecture, we denoted this as BCJ gauge. And this is obviously related to the BCJ identities. So, well, we are seeing some very beautiful structures, and this was all hidden before. But yeah, but I'm jumping a bit, and let's have some tea. Oh, should I continue? Or?
No, you can have tea after that. You can continue.
Carlos, the infinite tension limit, is that, can you get these from
Oh, okay, yeah. People nowadays call these guys the scattering equations, right? It's but in this context, they are nothing more than the statement that total derivatives vanish.
Right, but can you get all these relations by starting with, you know, this integrated vertex operator which doesn't have the d theta term and which has p, the infinite tension version of this? Do they give the same relations, or?
That's the paper that Umberto wrote, right? He essentially, well, the result there was, since you have this infinite tension limit, you never see double poles because you don't have the pi m and things like that. So you always get these scattering equations.
I understand, but the relations you get are all the same. It's just
The result is the same. It's you simply you basically copy these results and kill the double poles and do things like that, and then the result that you get is essentially the same one that we got. But yeah, the scattering equations, you can get them from the vanishing of these guys at tree level, and the same thing at least at one look, you can also show that it's nothing more than just that. But one thing that I should say here is that we never need to use numerics to do these computations. And everything is done algebraically and no numerics is involved. So let's have some tea. So now I'm going to talk about these superfields that denote KP and BCJ gauge. And I already defined here this set of multiparticle superfields that I'm going to, sometimes it's convenient to refer to the whole set as KP, and you don't really specify which object that, which particular superfield that you are talking about, but you think of as a collection of superfields. So that's the definition of this KP.
What is BCJ? I mean,
BCJ, it's Bern, Carrasco, and Johansson. And yeah, BCJ stands for these people, and I think I will try to talk about the BCJ identities from the field theory perspective using the pure Spinor cohomology formula that I hope to derive the beginning of the next lecture. And yeah, so that's the BCJ, but for now BCJ, well, it's, if you already know what BCJ is, good. If you don't, it's also good. And so the purpose of this extension after T is to explain how to get rid of the heads in the V's, or generally speaking, how to get rid of heads in KP, where I talk about everything at the same time. And we when when we started to look at these superfield, multiparticle superfields, it was around 2010. Yes, 2010. And we noticed that there was something happening with the V-hats that led us to consider the type of structure that I'm going to mention now. But the realization of a gauge happened just a few months ago, in 2015, in a paper that we wrote in October. So these things keep simplifying over time. It's, there is so much structure in this multiparticle setup that whenever you have a fresh look into these things, you can simplify it even more, and it's very rewarding. And so let's I will start with the original motivation from 2010, which is we now know the BRST variation of the V-hat superfield. It's something like V1, V2, 3 plus V and plus and curiosity led us to consider linear combinations of these guys that would make the BRST variation vanish. And it turns out that this is zero. If you simply use the symmetries of the lower multiplicity V's. So this is telling us that there is still some BRST exact. Yes, okay, so this guy is BRST closed, but the conformal weight of this V-hat is different than zero, so there is some BRST exact quantity hidden inside this V-hat. And since everything is cohomology in nature, that led us to consider, okay, let's try to get rid of this remaining BRST exact piece from V-hat. And that was the original motivation. But as I said, now this is understood as a change of gauge, and I hope that this new view will become clear perhaps at the end of this segment or the beginning of the next lecture. Okay, so this is true, and we already know that V12 is antisymmetric, right? And okay, so we have antisymmetry and the cyclic symmetry, the cyclic sum goes to zero. It should ring a bell that this is related to Jacobi identities. Right? Because if you have a structure constant like this is antisymmetric, and it also cycles. If you contract now, if you do this A3B, this one plus cyclic 1, 2, 3, that's 0. That's the Jacobi identity. And okay, what's the structure of these what can you expect in general? What are the symmetry properties of these objects? You can also consider V hat with 4 labels and what are the symmetries that they satisfy? Just as a general question, if I'm allowed to say, this is, suppose you define this as, say, T 1, 2, 3, 4. Everybody knows by heart these two Jacobi identities, right? It's antisymmetric, but what about this one? Is it obvious? What are the symmetries that you get from these? It wasn't obvious for us, but we played the same game with the rank 4 V hat, and we discovered that the symmetry. Okay, the symmetry related to this guy is actually that one.
So these are the free index C, right?
Yeah, there is a free index everywhere.
Sorry, what is L1 to A?
People usually write the structure. Okay, so I didn't say this is the structure constant of a Lie algebra. And people usually write as FA1, A2, and A3 and stuff like that, right? But whenever I have a particle label, I simply write the particle label and I don't write the A associated to that. And when there is a free label that is not set to any particle, I just write the letter A or B or C. So for example, this one is contracted, A and A here. So it's that's why it's A.
And this has to do with B hat 1 to 3 or not?
Yeah. The relation is that the symmetries of these objects are the same, right? So this one corresponds to that symmetry. That one
Okay.
is this symmetry here, and that's
So V hat will be is antisymmetric in first 2 indices.
yes, yeah, good. The symmetries of these of these objects is, I don't know if I'm allowed to say it's recursive or it inherits the lower rank symmetry. So this guy is antisymmetric in the first 2 labels, and similarly when you talk about the V 1, 2, 3, 4 V hat, that guy, it will inherit the symmetries of the first 3 labels from the lower.
But your T here is it analog of V hat 1, 2, 3, 4?
No. T here, I just okay. I'm committing the same mistake that I did yesterday, and I define these.
Yeah.
Just a definition. I say it's T with 4 labels that I construct out of these structure constants. And I ask, what are the symmetries of this guy? So it will be antisymmetric here because of that. It will cycle to 0 to 3 because of that. And then there is an additional symmetry that I wrote. It's 4, 3 plus it took us a long time to find these relations discussed in the math literature, but they are known as, well, generalized Jacobi identities, as you would kind of expect. And you can see the type of discussion from the mathematical point of view in a book called 3D Algebras by Hoytenauer. And I'm going to just say a few words about some.
This equality, this zero vanishing for 3 parts of f, that does not follow from Jacobi identity somehow manipulative?
It's precisely the Jacobi identity obeyed by the structure constant.
No, but the one having 3 parts of f, that must.
This one?
Yeah, this.
Yes. It's also. If you just plug these and you notice that these guys are anti-symmetric and they satisfy these, then these identity follows.
But you have summed over A and B, right? So
Sum over.
A and B summed over. Right?
Yeah, A, B, and B are summed.
Now, I'm saying this is not a new identity, right? Once you know antisymmetry of structure constants in Jacobi identity,
Yeah.
everyone else follows, right?
Yeah.
All the others follow.
Yeah. It's not something new, but it's still a nice structure to know. And in fact, what I'm going to show is what I think it's a very nice characterization of the general identity for multi-particle labels that I learned from that book. And I'm doing this because it will involve some abstract manipulation on multi-particle labels, which I'm going to define now. It's called the Dinkin bracket. Say L of a multi-particle B. Well, this is called Dinkin bracket. Perhaps it's Y and I here, but let me see if I get the spelling correct. Well, it doesn't matter. It's called Dinkin bracket, and it's defined as say now this is a general multi-particle label, but you can define recursively as L acting on U 1, 2. It's the standard bracket, so it's 1, 2 minus 2, 1, and L acting on 3 labels. That's defined as a left to right bracket. So it will be something 1, 2, 3 minus 2, 1, 3 minus 3, 1, 2 plus 3, 2, 1, and so forth. So you get the pattern here. It's, you simply write down the general bracket. You start with 1 and 2, and then 3 close, 4 close, and then n close. So that's called the Dinkin bracket. And these symmetries, they can be written as in a very convenient way that you can have these. Well, you can understand from. Well, I'm going to draw these diagrammatic. then there is this diagrammatic interpretation of the labels that of the symmetries that I'm going to explain now. So if you define these as, say, T, you say it's A with that multiparticle label and linking bracket of B, so that this is that. And now the generalized Jacobian identities is a statement that this guy is antisymmetric in A and B. So this is equal to minus, now it's B, linking bracket of A.
Okay, so what is the figure that you have drawn? I missed that.
It's called a planar binary tree, but right now it's just something that, well, I use it to motivate this relation. But
So A and B are multiparticle sets?
yes, yeah. So for example, let's just check that this is.
So these are multiparticles without brackets. Just
Yeah. So these are multiparticle labels,
okay.
but without brackets. And I realized that I didn't emphasize enough how you can get rid of the brackets, but it's going to follow soon.
What is T? T is as defined.
T is yeah. I should use a no. It's the same one. Yeah, because let's see what happens with this. So suppose A is 1 and B is 2. That okay, I didn't say that. Well, with L acting on a single particle, it's just the particle. So this will tell you that it's antisymmetric. So it's okay. So let's do A 1, 2, and then B equal 3. So that's 1, 2, bracket of 3, it's 3, minus T3, bracket of 1 and 2 is 1, 2, plus minus, and then because of that it becomes plus. And then if you rewrite, well, that's the Jacobian identity. And if you do that in general, you get all the.
So the first one is A equals 1, B equals 2. That is T1, 2.
Yeah, okay, I'm making the same mistake as before. So this one is for A1, B1, you get that. A1, 2, B3, you get that. And you can convince yourself that you can do this to get the identity that I wrote there before, and you can get the general thing.
B2 or B1? First one, A1.
Oh, okay.
So you could have written down that equation without drawing this diagram, right?
Yeah.
B A of LB is equal to minus K B of L. This is an idea.
Yes.
Okay.
But provided you know the definition of T. This is one.
Yeah, so T is something which satisfies that identity. That's what he said. Yeah. So this is one construct.
So that defines the entire stuff, right? Given the linking bracket and that relation, we should be able to derive given that.
No, but there T is defined only for 4 indices.
What?
No, now it is defined for any multiparticle entity.
So it has so T there,
Yes.
A, L, B, for arbitrary multiparticle indices.
Yeah.
It has to be constructed with an object with 3 indices, which is antisymmetric in first two.
Yeah. Well,
This
say this is corresponds to T12, and then that is simply the statement that it's antisymmetric, and then this is T123 plus T231 plus T312 equals 0, and those are these identities here are the ones that are generated by that.
no. In the second example, T123, what is the definition of T123? Is it constructed of L square?
2F.
It's
So basically what has to
So okay, so since I thought that okay, since this is so what this is that 1 2 a 3b plus f 2 3a f a 1b plus f 3 1a f a 2b, that's 0. That's the covariant. And if you just use this definition here, that corresponds to that. And that's what I did. And if you, okay, so if you define in general A3B, B4C, C5D, and so forth as T1, 2, 3, 4, 5, and that's what that identity is telling you. What are the symmetries of these guys? And it happens that these symmetries that are generated by that identity are precisely the identities, the vanishing condition of the BRST variation of the V's. So it's
So for multi-particle, V hat will always be constructed out of V1 to this way. What is the analog of L there? V?
so V hat is constructed like this. You put hat here and everywhere.
Now I'm asking, see here you are talking about the symmetries of T, right?
Yeah,
For which you have given a general definition.
yeah.
And that definition involves L, which has 3 indices.
No, there is no L here.
Yeah. Huh? Structure constant F.
Yeah, okay, F.
Oh, F. Oh, F. Oh, I'm
F,
sorry.
F.
Yeah.
Okay. Okay, now I'm asking this symmetry properties of T that we are discussing. It is relevant because we are going to use similar symmetry properties for V hat.
Yeah.
That is a symmetry property, what you are written there.
Yeah, so those are for V hats.
Yeah, perhaps
For arbitrary number of multi-particles levels.
I guess it's not clear what's happening here because when you go through the OPE exercise, you find this V hat, you check this, that's true.
Okay.
You get that. And you go through the exercise and do this for the rank 4 guy. That's 0. And you do that for 5 and you get some identity there. And in 2010 we were looking at these symmetries and we were kind of lost, but we knew that they were interesting. There was some structure, but it took us some time until we found the connection. And actually this connection was made in 2012, in March, I think, 12/03 something. We noticed that, okay, the symmetries that we are observing experimentally just from constructing these guides are the same symmetries of a structure constant. And then that's where the BCJ story really, okay, but
So V hat will also have a construction in terms of something like F here, structure constant.
no,
It just satisfies the
it's just
symmetry
that,
properties of T.
yeah, it's you want to characterize the symmetries. It's the symmetries are the same.
But this is not a proof, right? Because
It's not a proof.
yes. So how do we know that this will definitely carry through? Like you can use. This. How are you sure about that?
For all
Yeah,
the chemicals.
I guess it's not a mathematical proof, but it's a physicist proof. Yeah, and, that's an open problem. Just find the mathematician to prove this.
Also, here, all the others involving 3 or more F's follow from Jacobi identity, right? But here, these relations don't follow from each other.
Yeah, they're following from some.
So they are independent equations, like this.
Oh, yes.
The vanishing with 4 insertions does not follow from 3, but the Jacobi equation, the general Jacobi identity for 4 follows from 3.
Yes.
So these are all independent equations.
Yeah, so what I'm saying here is that the symmetries you see here are the same symmetries that you see there, but there's no.
Here is only one equation carries non-trivial information, others are trivial information, but here you carry non-trivial information.
Okay, so for the first one, 1, 2, 3, you said that it is antisymmetric in the first 2 indices. So then without Q it is 0?
No.
It probably is, but I should say, what I'm really sure is that, I am not really sure about how many redefinitions I did here anymore, but when I finally arrive at the definition of V1, 2, 3 without the head, then that's definitely the case. That you have all the Jacobi symmetries in these kinds. And
because you have subtracted off some things. The BRS exact states you have subtracted off.
Yeah. So let's do this for once. And this bracket notation, right? And okay, so that's another way to motivate looking for Jacobi identities, simply because we have brackets, the bracket notation, right? Say what is happening is that we are defining something like this and recursively. So we are going to have this and so forth in general. And then you look at that and you simply say, well, this must satisfy some. No, it's you are motivated to look for Jacobi identity simply because of the notation is telling you to do that. So that's another way to see that. And what happens is that you do this plus cyclic, and you will get that the end result is some factor 3 times the derivative of an object which is called H1, 2, 3. And you do the same for the object, for the superfield with the index m plus cyclic. That's 3 times momentum m 1, 2, 3 H 1, 2, 3 and W and F are invariant, so they cycle to 0. And now I still need to tell you what H is, but you immediately see from this structure here is that when you define a vertex operator with these superfields as the coefficients of the conform weight 1 variables, like that, and then you do the cyclic sum, you can interpret the result as a total derivative, because this guy, okay, so you will have something like this. It will vary to something, it will vary to this one, k 1, 2, 3 of age 1, 2, 3. So that's also a way to try to motivate that there is a gauge, a change of gauge happening because of this interpretation here. That's a total derivative of age 1, 2, 3. And
sorry, I didn't understand this hat on A, alpha and AM.
yeah, the hats are telling you that we still didn't do the subtraction, the redefinitions to get rid of various the exact parts. And these guys are defined by these recursions here. Okay, so these things are I guess they are. You can look at this paper here from last October, just to if there is some. Yeah, it's. I hope that the paper explains better than. And okay, so we get these ages, right? You simply and that's a mathematical problem really. You use these definitions, you do the cyclic sum, and for example, it's very non-trivial that you get a momentum factorized out of this sum. It's very, very non-trivial. You need to use all kinds of identities to get these momentum factorized like that. But it happens. And it happens for higher ranks as well. From this structure now, you can find the redefinitions that will get rid of of the hat, and the way to do this is say now, for example, the A without hat 1, 2, 3. Alpha is defined as the A hat alpha 1, 2, 3 minus or plus V alpha age 1, 2, 3. And there is also some mathematical thing going on, because suppose that I just want to label, to give a name to this identity. So, for example, the antisymmetry of T, I call that this is generated by L2. So L2, V2 acting on T12 is defined as you do this sum here, and then that's 0. And then similarly you act with you find L3 to do a cyclic sum, and L4 to do that sum over there. And once you have this definition, you can observe that this guy there, L3 acting on H1, 2, 3, that's 3 times H1, 2, 3. And L2 acting on this guy is 0. And that's true in general actually, at least as far as we check it, like rank 5 I guess, that's true in general. The rank, the multiplicity P of H, I'm going to write something like that, satisfies that LP is P times, where P now is the multiplicity, is the rank of that guy, P, like that. And for P equals the rank there. And when, okay, so I would say that Q. So for Q, for the rank P, Q, that's true. And then when Q is less than the rank, the multiplicity of H, then LQ annihilates this guy. And yeah, okay, so this is consistent with the redefinitions, and they simply come from all this, but we still don't have a mathematical understanding why this is true, or what's going on here. It will be very useful to have a better understanding of that. So that's another open problem. And I'm going to show to you a few solutions, how these A's look like, and because that's also another open problem. We know the solutions up to rank 5, and we started to do the rank 6 analysis, but there must be a general closed formal solution for these guys that implement these redefinitions. And so right now it's a very technical part of these definitions, but it's an open problem. So if you solve it, then just send me an email. It's oh, okay. So for example, this is how the redefinitions look like at rank 3, and how do they look like at rank 4. So for example, I'm going to do this for M A 1, 2, 3, 4. The redefinition is given by 1, 2, 3, 4, and just to show to you how beautiful the structure is. It's very recursive. And once you do this redefinition for the rank 4 part, for the rank 4 multi-particle label, you get that this guy satisfies the rank 4 Jacobi identity. And yeah, this is I think this is interesting, and actually well, this is very technical right now, but there are some heads in these guys. And I will just write down the recursive structure that we found for these ages. This is a very recent analysis, because when we started this business, we simply had these, what we call ages now, but we had the full expansion without any order, any organization in terms of recursive constructions. But now we have that, at least for the first cases, and it will be very nice if this is solved in general. So I will just tell you how the solution looks like. And minus a b. That's the definition of this hat, h hat. And I need to tell you what this age is. And that's where we have just lower case examples and another really recursive solution, but it depends on another type of object that I'm going to define later. That's the solution for h12, and the solution for h1, 2, 3, 4 is 1 over 4, and then h prime, it's another guy I'm going to talk about. H prime 3, 4, 1, 2, and there is also an expression for H1, 2, 3, 4, 5 that you can look at the paper, but this H with 3 slots and H prime are defined by so H prime, A, B, and C, now with particle labels up to the order that we considered. That's the 3-point amplitude, actually. I'm going to add MN, C, and then plus or minus F, W, A, gamma, M, W, D, A, C, N, plus cyclic in A, B, and C. And just out of just a random observation, if you use single particle labels for A, B, and C, 1, 2, and 3, that's the expression for the 3-point amplitude. So there is something going on in terms of superfields, and then.
Sorry, what is the statement?
Yeah, so H prime 1, 2, 3 is well, it's a superfield expression, so these guys depend on theta. But if you evaluate at theta equals 0, you pick only the first components of these superfields, and then what you get here is minus, well, you get EM1, EN2, FMN3 plus cyclic, and these guys become chi1, chi2, A3N plus cyclic. So that's precisely the 3-point amplitude. There is something beautiful going on here, but it's still work in progress. But
the first equation here, H is that H prime 1, 2, 3?
it's
One third.
no. Yeah, okay, so h prime, it's, yeah, so h prime, but in this case, what will happen is that h prime is equal to h when the single particle labels are, well, when the labels are single particle. But, and then the last thing is, what's the definition of h prime? A, B, C. It's, so it's, so that's h. So h prime is that h plus.
So what is h 1, 2, 3 without bracket? 1, 2, 3 without bracket.
That's the definition.
Okay, so the definition here is follows the definition for that I mentioned before. That's defined as you remove all the brackets when there is a single particle label in the last slot. You define that as something without brackets, and that is
The last slot is single particle.
yeah. So it's p minus 1, comma p.
But all of them, they are.
These are all single particles. Here the labels are all single particles, right?
See,
1, 2 are all single particles.
yeah, but the whole thing is a multi-particle.
Yeah.
So
Yeah,
it's
but
one.
individually they are single particles.
Yeah, but if you just zoom in one of these, that's.
But all these two equations that you have written there, left bottom corner.
Yeah.
So these are all last 10 single particle.
Yes.
So they are all like h 1, 2, 2, 3,
Yeah.
4.
Yeah. But I didn't write here, but we also know 1, 2, 3, 4, 5. Okay, so this is.
Why do you invent a new notation for that?
It's something that we came up with this as a way to organize the computations, and it's a way to try to see the structure behind these solutions, to try to find some answers for the general case. But this is very technical, I realize, but it's some yeah, so just a curiosity actually, but and then plus cycle A, B, and C. Yeah, so we have solutions that satisfy this structure up to rank 5. And yeah, so that's how you redefine your superfields. You get something like that, and at least we know the general structure of these corrections here. But what remains to be done is to find the general expressions for the ages, and up to the point that we look at, they satisfy these. So the next, okay, so I'm just going to write down the last blackboard here, and as the starting point of the next sector. So what we arrive at today here is that now we have superfields that satisfy all the Jacobi-identities for all the, they satisfy all the Jacobi-identities, and they have nice BRST variations. So I will just write down the BRST variation of the general guy here. This is.
So if I understand right, in that equation, the H prime ABC should be under bracket, within bracket?
Yeah,
The left hand side.
the bracket is
On the left hand side.
no, it's A, comma B, comma C, where A, B, and C are
Okay.
bounded.
And those are, okay, I see.
This is the first equation here, right? H1, 2, 3 bracket is 1/3 H prime 1, 2.
So this is you are generalizing the definition without of in with H
Yes, yeah.
with okay without bracket, index without bracket. See, you defined H prime with 1, 2, 3 without bracket to be what? I'm confused now.
H prime never has bracket.
H prime never had brackets. Okay. I see.
So what you see here are the brackets, H brackets, and H bracket is defined like this. So this is recursive. I mean, the guys that you see here are of lower multiplicity that you already know, so it's fine. And then this guy, I didn't tell you, but they have this form as explicit computations show, and they can be written in this form in terms of this H prime, and they have this form, and H prime is defined like that, and H, so everything here is of a lower multiplicity, so you know it, and then this H ABC is defined as this expression there, which by the way reproduces the 3-point amplitude. Multiplied by Vj alpha, where gamma here is the set of labels that start at j plus 1 up to p, and p of gamma is the power set of this set, and alpha belongs to the power set, and beta is gamma without the set alpha. So that's the general expression for the BRC variation of E, and there are similar expressions for the other superfields.
What is the last B1 to j minus 1 and then?
Yeah, so multiply, so the blackboard ended here, but so it's V1 to j minus 1, and then the set beta, and then multiplied by this part here, V of j, and then the set alpha, where the sets alpha and beta are defined like this. Alpha belongs to the power set of gamma. Gamma is of this form, and beta is gamma minus alpha. So it's but that's true. And so the question for mathematicians is, if you have this power set structure of BRST variation, how can you show that the right hand side satisfies Jacobi identities? We know it's true by observation, but there must be a general proof for that. Yeah, okay, so, and then this guy satisfy all the Lie symmetries. Well, in particular, now I'm going to use the notation that I done before. It's for all P. So yeah, I guess, are there any questions? It's just okay. Yeah, I think that's a natural stopping point. This notation here means, for example, if Q is 1 and 2, then Q, this notation here simply means that
Oh, that I
it's
understand.
the multiplicity of.
Okay, that's fine. I thought Q is the BLST operator.
Oh, no.
Earlier you have for P less than Q, right? And for P equal to Q, there is an eigenvalue.
Yeah.
For P less than Q, it's 0, but P equals Q is also 0.
What is 0? The earlier relation had
Earlier you
that
had
was for something else.
Yeah, so for example, L4 is that 4-term identity with T12, 34 minus T12, 43, and plus other 2 terms. And this guy annihilates V1, 2, 3, 4.
Oh,
So it's
very individual term is
so there is a lot of mathematical structure here, and you can even think about this without pure spinors. You simply start with a definition like that, you use the case of motion at the linearized level, and all this follows. You don't really need pure spinors for that. But it was during the computations with the formalism that we landed on this structure, but the structure is there independently of pure spinors. And in particular, this is about super mu's in 10 dimensions n equals 1. So there must be a dimensional reduction and the same of these, and you will find these structures in n equals 4 super these as well. Some guys.
But once you have this structure, you can also put it back and get the higher derivative corrections, right? In the convolution amplitude, once you put, by expanding the convolution factor, you can get the higher derivative corrections also. So it's not just super-Poincare.
Yes, it's true.
Once you do the integral and expand.
Yeah, once you do the integral and expand.
But these corrections could be of this form multiplying some matters.
Yeah.
But what I think would be interesting is to study the dimensional reduction of these, and this will also capture the multiparticle structure of n equals 4, for example. And the next lecture I will talk about the field series amplitudes that you can guess from this structure, and then I will write down the string correlator using this language, and yeah, that's probably it. And then there is also another type of structure that you can construct from these, which are called the Berns-Gilly currents. That you start, say for example, V12 you divide by S12, and because then Q of this is just V1, V2. And there is, and you can do that for higher points as well. You divide V1, 2, 3 by S12, S1, 2, 3, and then you sum 3 to 1 over S to 3, 1 to 3, and then Q on this combination here is V1, V23 over S23 plus V12, S12, V3. So you get a nicer structure, and actually you define we define these as M's. So and then you get the structure that this equation satisfies is that M of a multi-particle label is given by a sum over all the concatenations of the label Mx and Y. And this is precisely the type of equation that comes from string field theory, for example. It's QV is V squared. And then that you can construct a generating function of these M's, and that generating function will solve the nonlinear equation of motion. Super N-wheels, and I hope to have time to explain that. But it's very interesting because you start with the linearized equation of motion. You go through all these steps. You define these M's like this. There is a general definition for that. They satisfy this equation, and now you define a generating function where you expand these in terms of the algebra generators. So, for example, you define a vertex V like that by using M1 T1 plus M12 T12 like that, where T are the generating the algebra generators, and so you sum all of them. They satisfy linearized the equation of motion. But then when you consider the equation of motion satisfied by the sum, it solves the nonlinear equation of motion. So you recover the nonlinear structure by summing over all amplitudes, linearized. So you go back, you do the full circle. You start with the nonlinear equation of motion, you linearize to compute amplitudes, you compute all the amplitudes, endpoints, you know the general thing, you sum over them all, you recover nonlinear. It's interesting, and it's totally independent from pure spinors, and there must be a dimensional reduction, understanding of these, and these structures are just starting to be studied now. There are a lot of open problems, and I'm sure this will give more interesting things in the future. So it's fascinating.